Hey everybody, welcome back. This is lesson 5 in unit 6. Today's lesson is called Real versus Ideal Gases and the KMT. Now, in the last video, we covered the combined gas law, which according to the reference table was PV over T equals PV means P2 V2 over T2. Now this combines all three of the gas laws, and depending on whatever question you're given, if you're given, five of the six variables, you have to use the whole thing. If you're given 3 out of the 4, that means something wasn't mentioned or something's held constant. So if something's not mentioned or held constant, you can ignore that from the equation. So again, don't need to memorize it on the reference table. Now, our last topic in this unit covers real versus ideal gases and something called the kinetic molecular theory. Now, the kinetic molecular theory, or the KMT, predicts the behavior of the ideal gas particles, their pressure, their volume, the temperature, velocity, frequency, and the force of the collisions. So basically, the KMT tells you how an ideal gas particle will behave. Now, there are 4 statements of the KMT. Statement number 1 says the ideal gas particles are in random, constant, straight line motion. So basically what that means is that these gas particles move in straight lines until they hit something and bounce back. So perfectly straight lines, they're not going towards anything, they just do whatever they want in a straight line. So what you don't see is these weird patterns. All they do is go straight. Statement number 2, ideal gas particles collide with each other and transfer energy, but the total energy in the system remains constant. So what that means, it's kind of like Newton's cradle, which is this GIF right here. You pick one up and you let it go. Energy transfers one way between each of the spheres, knocking that last one out, and then it comes right back, and these energies going back and forth. So these gas particles, the energy is being transferred from one to another, but the energy that's in the system, in the container, does not change. It's just moving from particle to particle. Statement number 3 says ideal gas particles have no intermolecular forces. So remember, intermolecular forces, or IMF, are how different molecules interact with each other. So here is a picture of water. And to remember, you have those delta negative and delta positives. And here you have 2 water molecules interacting with each other, with the partially negative and the partially positive lining up with each other. Now, according to the KMT, ideal gas particles do not have these intermolecular forces. Gas particles do not interact with each other. They don't attract each other, they don't repel each other. That's what the KMT says. Last statement of the KMT says gas particles have mass, but no volume. So because they're very far apart and relative to their size, we can totally ignore their volume. Now, those are the 4 statements of the KMT. But the problem is, again, the KMT talks about ideal gases. Ideal gases don't exist. So why even bother talking about the KMT? Now, here again are the 4 statements. There are 2 that are not quite right, or 2 that don't apply to real gases. So which 2 do you think don't make much sense based on what you know about gases and what you know about chemistry? So our problems are with statement 3 and with statement 4. Statement 3 says ideal gases particles have no intermolecular forces and therefore do not attract or repel one another. Now, the problem is they do have these forces of attraction. So if you have, go back to the H2O, you have like that, you're going to have these water molecules interact with each other. The water vapor molecules interact with each other a different way. Other gases do that too. Real gases do have forces of attraction. So this is a great slide. Statement 4, gas particles have mass but no volume. If you think about it, gas definitely has volume. If you blow up a balloon, you can see that. So real gases do have significant volume. You can't just say it doesn't exist. You can't just throw it out because you don't feel like dealing with it. It's there. It exists. So again, that's reason number 2 why ideal gases don't exist. Okay, now a real gas can act as close to ideal as possible if they are in the right conditions. So they can be it has to be low pressure and high temperature. So that's what allows a gas particle to be most ideal. And so this word, plight, will help you remember that. And so what it stands for is pressure, low, ideal gas, high temperature. Now, on every gas law homework, you should use Kelvin, combined gas law formula, and plight. So basically what this means, every KMT question basically is answered by this. So you act like an ideal gas with low pressure and high temperature. So if you think about it, if you have low pressure, particles aren't being forced to do anything. They can kind of go wherever they want. So that's why low pressure kind of makes sense. If you have high temperature, remember the higher the temperature, the higher the average kinetic energy. So the faster you increase the speed, the faster they move. If particles are moving quickly, it's harder for them to interact with each other. So if they're not being forced into a small container and they can move really, really quickly, that's what allows gases to be the most ideal. So low pressure, high temperature, again, plight. Pressure low, ideal gas, high temperature. Again, literally 90% of the KMT questions can come from this word right here. Just some other gas facts. So if a gas acts most ideal at low pressure and high temperature, a gas acts least ideal, or most rare, in the opposite conditions, so high pressure, low temperatures. Hydrogen and helium are the two gases that act most ideal because they are the lightest. They're also the smallest. And then lastly, when we covered moles, we covered this. Avogadro's hypothesis states that you have equal volumes of gases. If you have equal volumes of gases under the same conditions, you have the same number of molecules. Again, you can go back to the mole-volume conversion to kind of talk about that more, but that's basically it. So basically all we learned today, the 4 things of the KMT, the 2 reasons why ideal gases don't exist, and then how they can act most ideal. So that's pretty much it. Stay tuned for Unit 6 review videos. That is it. Have a wonderful day.